Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with our last topic. In the last lecture, we discussed photoelectric effect. So let me first write continue. So today we continue the photoelectric effect. The last time we defined photoelectric effect, we said in this effect we shine light on a metal surface, and if its frequency is sufficient enough, electrons are ejected. Those electrons are called photoelectrons. Then we discussed its experimental setup. We said how we explain or study photoelectric effect. In photoelectric effect study, what we do, we have a vacuum tube in which we have two electrodes. One is called emitter, second is collector. Then we shine light on the emitter, and if its frequency is sufficient enough, electrons are ejected, they are collected by the collector, and we have a current in the external circuit which is called photoelectric current. Now we establish potential difference across emitter and collector by means of this potentiometer or battery. Then we said that the voltage across the emitter and collector is algebraic sum of two voltages. One is externally applied voltage, which is read by the voltmeter, and second is the contact potential difference, because the emitter and collector are made up of different materials, so there is some contact potential difference between them. Then we discussed some experimental findings. So when we plot photoelectric current versus potential difference, we have a positive zone of the voltage, negative zone of the voltage. I have discussed it already. In this zone, the voltage is opposing the motion of electrons. In the positive zone, the voltage is helping the motion of electrons. Then we discuss these curves and we established certain results. One conclusion was the saturation photoelectric current is proportional to the intensity of light, because we said and discussed that in curve B we double the intensity, so saturation photoelectric current doubles compared to situation A. But the stopping potential, the reverse or negative voltage at which, I should say, minimum reverse or negative voltage at which photoelectric current becomes zero, it is independent of the intensity of light. And next thing was, since the kinetic energy is proportional to the potential stopping potential, the kinetic energy of the photoelectrons is independent of the intensity of light. Now there is more to it. We have one more experimental finding. So let me discuss that. First select the color of my page. I will use this color. So let me use here yellow color. So what is the next experimental finding? So if we plot the stopping potential, stopping potential V naught, let it be in volts, versus the frequency nu for some metal surface, we get a straight line like this. So experimentally we see that stopping potential has a linear dependence on the frequency of light, and it has certain slope. So for different metal surfaces, uh, you can have different slopes, but things linear relationship will be true for all metal surfaces. Now this frequency we call mu naught, the frequency at which the stopping potential is zero. This frequency is called threshold frequency. This threshold frequency is the characteristic of the metal surface in question. That means every metal surface will have uh, its own uh, threshold frequency, right? Now, what is the importance of threshold frequency? You see, at frequency equal to threshold frequency, stopping potential is zero. And from this relation, you can see kinetic energy, maximum kinetic energy of the electrons is equal to EV naught. That means for threshold frequency, Kmax is also zero. So for nu is equal to nu naught, Kmax is zero, right? Because V naught is zero. That means at threshold frequency, electrons are not able to move to the collector. Hence, there is no photoelectric effect. There is no photoelectric effect at frequencies less than or equal to threshold frequency. So this is one more experimental fact about the photoelectric effect, that for every metal surface there exists a threshold frequency. If the intensity of light is having any value, it can be any intensity, but if the frequency of the light is less than or equal to threshold frequency of the metal surface, there will be no photoelectric effect. Only for frequencies greater than threshold frequency, light can, in a particular metal surface, eject electrons and photoelectric effect will take place. Now, question is, can we explain these experimental findings using wave theory of light? Now we will see that, let me write, explanation of the photoelectric effect using wave theory of light. So if you take light as an electromagnetic wave, you cannot explain photoelectric effect. We will see that the failure of classical wave theory is not a matter of small numerical disagreement. The failure is total and indisputable. Here are three problems. The three problems we have in explaining. So, three problems arise. Let me discuss those problems. Let me change the color of my page. Let me start this color. So, what are the problems? First problem which we face and we try to explain the photoelectric effect using wave theory is called the intensity problem. What is the intensity problem? In wave theory, we have an oscillating electric field. We have electric field is oscillating in a wave with time and with position, and that electric field has some maximum value which I call em, which is called amplitude of the wave, right? And it has also oscillating magnetic field in it which is perpendicular to the electric field, that has also a peak. We are talking now in terms of electric field. Now, according to wave theory, if you increase the intensity of light, this intensity of light is proportional to square of the amplitude of the wave, right? So when you are making light more intense, according to wave theory, you are actually increasing the maximum value of the electric field. That means all other values of the electric field are increased. You are increasing the electric field in the wave. Now you know also this electric field, when light shines on the metal surface, the electric field in the wave will exert force of electric nature on the electrons. If a charged particle Q is placed in some electric field E, then that electric field will exert force of electric nature on that particular charge, which is given by QE. That means the magnitude of the force is QE, and the direction of the force will be in the direction of the field if Q is positive, and opposite to the field if Q is negative. So when you apply this idea to the electron in the metal surface, so when you shine light on the metal surface, the electric field present in the wave will exert force of electric nature on the electrons. So though that force will do work on the electrons that increase the kinetic energy of the electrons, right? So when you increase the intensity of the light according to wave theory, what should happen? Electric field in the wave should increase, and that electric field will lead to increase in the force experienced by the electrons due to the electric field. Hence, the kinetic energy of the photoelectrons should increase. With increase in intensity, the kinetic energy of the photoelectrons should increase, right? Increasing intensity means increasing electric field, means increasing force on the electrons. Hence, the kinetic energy of the photoelectrons should increase with increasing intensity. But what is the experimental finding? Experimental finding is the stopping potential and the kinetic energy of the photoelectrons is independent of the intensity of light. If you change the intensity of light in the photoelectric effect, there is no impact on the kinetic energy and stopping potential. As we have discussed these curves, where doubling intensity in curve B, but the stopping potential and hence kinetic energy is unaffected. So it is one issue which is called intensity issue. You can see there is total disagreement between the wave theory and the experimental finding. It's not a small variation. There is total dispute. Experiment says Kinetic energy of the photoelectrons is independent of the intensity. Wave theory says kinetic energy of the photoelectron should increase with increasing intensity. So let me discuss the second issue which we face when we try to explain photoelectric effect using wave theory. That's called the frequency problem. What is frequency problem? According to wave theory, the photoelectric effect should occur for any frequency of light, provided only that the light is intense enough to supply the energy needed to eject the photoelectrons, which is evident from this explanation in part first of intensity problem. Because if you want to pull electrons out of the metal surface, you need force, right? And force you can adjust by adjusting the intensity. So there is no question of frequency. Photoelectric effect, according to wave theory, must occur for all frequencies of light. For any metal surface, only the intensity should be adjusted so that the field and the force are able to move the electrons out of the metal surface. So there is no idea or concept of threshold frequency. I hope you got it. Experiment says whatever the intensity, if your frequency is not greater than threshold frequency, then photoelectric effect is not going to occur. Wave theory says there is no idea of threshold frequency. Photoelectric effect should occur for any metal surface for all frequencies of light. Just it is a question of intensity. Intensity should be sufficient enough so that the field and the force are sufficient enough to extract or push the electrons out of the metal surface. Right? So there is another total dispute between experiment and theory. Then we have third issue. Now, what is the third issue? The third issue is like this. That's called time, the time delay problem. What is the time delay problem? Now, in wave theory, the energy is uniformly distributed over the wavefront. In wave theory, the energy is uniformly distributed over the wavefront. Remember, wavefront is the surface constructed by joining the points which have the same phase in the wave. So when this is metal surface, when light shines on it, now this light of some frequency shines on the metal surface, what will happen? Wavefront will strike the metal surface. Now there is some effective target area. What is effective target area? Now in this metal surface there is electron, right? Now this electron is available in certain surface portion, and that surface portion in which electron is available is limited, and it can't be much more than that of a circle of diameter roughly equal to that of the atom, because electron is in the atom, and that means it is confined within that space. So when the wavefront strikes that, the electron can absorb energy from a limited portion of the wavefront because it is available in the limited portion. Now understand this. Intensity is by definition power per unit area. Power itself is, if delta E is the energy transferred by the wavefront to the electron in time delta t, right? Then power is delta E by delta t. Now, if I solve for delta t is delta E by IA. Delta t is delta E by IA. Now, what is delta E? Delta E is the amount of energy, for example, in this case, required by the electron to leave the metal surface, right? And delta T is the corresponding the time in which it can absorb that much energy from the light. A is its effective area, the area from which it can absorb. I is the intensity of light. Now this A is already small, a small quantity, right? Now if I make I intensity of light small, it is adjustable. Adjustable. For example, you shine light on a metal surface, provided its frequency is greater than threshold frequency. So you are ensuring that photoelectric effect should take place. Now you can do one thing, you can adjust the intensity of the light to adjust the time required for the electron to absorb energy from the light, right? Now, when you do that, it is possible that you make this delta t 1 week, 1 day, 1 hour, 1 month. You have to only adjust the intensity, make intensity small. You can make time required for the electron to absorb the required amount of energy from the light large. So it is adjustable according to wave theory, right? If you are adjusting it to 1 day, then what should happen experimentally? There should be time delay of 1 day between the moment when light is impinging on the metal surface and the moment when electron is ejected. That means when I am shining the light electron should come out of the metal surface after 1 day, right? Similarly, if you make it 1 week, you shine the light on the metal surface. After 1 week, electron should come out. So you can make the time delay happen of your choice between the impinging of the light on the metal surface and the ejection of the electrons. But in practice, when experiments are conducted, no detectable time lag has been measured. No detectable time lag has been measured. Whatever the intensity, in practice, if frequency is greater than threshold frequency, whatever the intensity, there is no detectable time lag between the moment when light hits the metal surface and the moment when ejection of electrons takes place. So we say experimentally, the photoelectric effect is an instantaneous kind of phenomenon. So you can see another dispute. So we have these disputes in explaining photoelectric effect using wave theory. So we say wave theory fails. Wave theory fails in explaining the photo. How can we explain these experimental findings? Now, Albert Einstein in 1905 gave the explanation of photoelectric effect. So let us discuss that. Let me use white page for this. Einstein's photon theory. Let us discuss this. In Einstein's photon theory, which was given by Einstein in 1905, Einstein made a remarkable assumption about the nature of light, namely that under some circumstances it behaves as if its energy is concentrated into localized energy bundles, which we called photons. Right? So Einstein in 1905, to explain the photoelectric effect, changed the outlook of light. Previously, we thought it's an electromagnetic wave, but he said that under this certain circumstances, it behaves like a stream of photons, where photons are localized energy bundles. Energy of a photon, energy of a photon E is h nu, where h is Planck's constant. We have already discussed it with value, the small value 6.6 into 10 raised power minus 34 joule second, and nu is the frequency of light. You can see the energy of a photon is proportional to the frequency. Greater the frequency of light, larger is the energy of the photon corresponding to that light, right? Let me name it equation 1. Now, this notion that light is a stream of particles is in sharp contrast to the notion that it behaves like a wave. Remember, in wave theory of light, the energy is not concentrated into bundles, but is spread out uniformly over the wavefronts. Now, how this idea can explain the photoelectric effect? So let us discuss that. Now, if we apply Einstein's photon concept to the photoelectric effect, we write h nu is equal to phi plus k max. Let me name this equation second. What is h nu? It is energy of the photon, right? So, according to Albert Einstein, this equation 2 says that a single photon carries an energy h nu into the surface where it is absorbed by a single electron. This is important in this idea of photon in photoelectric effect. Single photon, single photon interacts with single electron, right? So when this photon strikes the metal surface, single photon with energy h nu interacts with single electron, right? Now, part of the energy, this one, phi, we call it work function of the emitting surface. Work function of the emitting surface. Now, what is work function? Let me first define it. This phi, which is work function of the emitting surface, represents the energy needed to remove the least tightly bound electrons from the surface. Remember, in the metal, electron is bound by attractive forces of the metal body. The first, this electron is to be freed from those attractive forces, only then it can move. So, according to this equation, Einstein's photoelectric equation, which is called, the photon energy is used up in two parts. Firstly, part of this energy, which is called the work function, which we defined as the energy needed to remove the least tightly bound electron. More tightly bound electrons require a larger energy than work function. So, part of this photon energy is first used in causing the electron to escape from the metal surface. It has to become free. Then the excess energy or remaining energy H2 minus phi becomes kinetic energy of the electron, which is K here. Here in this equation, K max represents the maximum kinetic energy that the photoelectron can have outside the surface. Now, if electron does not lose energy by internal collisions as it escapes from the metal, it will have greater kinetic energy after it emerges. So when we write in this equation K max, that means it is for that electron which experiences least uh, internal collisions as it escapes through the metal and which is least bound. Now, more tightly bound electron and the electron which experiences more collisions will have this term smaller, will have lesser kinetic energy. Misunderstood because energy is conserved. So, part of the energy of the photon is used in making the electron free. The remaining part of the energy h nu minus phi becomes the kinetic energy of the electron. Now, whether kinetic energy is small or less than smaller than maximum or by what amount it is smaller than maximum, that depends on the degree of boundness of the electron and the collisions which are experienced by the electron as it moves out from the metal surface. So you can understand why the electrons leaving from the metal surface has a range of kinetic energies. because the electrons are bound in the metal by different degrees, and the collisions experienced by the electron in the metal vary from one electron to another electron. Now let us see how we can, using this Einstein's photon idea, can uh, justify or answer these three objections which were raised against the wave theory. So let us explain. So let me explain that. Let me change the color of the page. Let me use green. Let me use black for the pen. So first thing, the intensity problem. Now, there is complete agreement of the photon theory with experiment. See, according to photon theory, if we double the light intensity, we double the number of photons striking the matter surface and thus double the photoelectric current. I repeat, doubling intensity means doubling number of photons. Remember, we said single photon interacts with single electron. So, according to photon theory, when we double the intensity of light, we are doubling the number of photons striking the matter surface. That means they will interact with double the number of electrons. So, saturation photoelectric current must increase. We're increasing the intensity of light, as is the observation from the experiment. We said that the saturation photoelectric current is proportional to the intensity of light. So doubling intensity means doubling the photoelectrons, doubling the photons striking the metal surface. So double the electrons will be ejected. So saturation photoelectric current will double. But we are not changing the energy of a photon, because remember, according to this photon theory, energy is equal to h nu. So when we are doubling the intensity, we are not changing the frequency. Hence, we are not changing the energy possessed by a photon. When we are not changing the energy possessed by a photon by doubling the intensity, we are not changing the kinetic energy, because we are not changing the total. So this portion of the kinetic energy is not going to change. So that answers the first issue. So according to photon theory, I repeat, doubling the intensity means doubling the number of photons hitting the matter surface, but we are not changing the energy of individual photons or the nature of the individual photoelectric process, which is described by this equation 2, right? Now, the second objection we explain, the frequency problem. Let us understand the idea of the threshold frequency. Remember, there exists a threshold frequency according to experiment, but wave theory discards that. According to wave theory, there is no such thing. Now, in Einstein's photon theory, if Kmax is equal to 0, remember when nu is nu naught, when from experiment, when nu is nu naught, stopping potential is 0, hence Kmax is 0, because Kmax is equal to EV naught. We have discussed it already. At nu is equal to nu naught, from the graph, stopping potential is 0 here. And when stopping potential is zero, that means K max is zero because K max is E naught. Let me move to my page. So when nu is nu naught, stopping potential is zero, K max is zero. Therefore, from Einstein's this photoelectric equation 2, what we get? We get H nu naught is equal to phi. This term K max is zero. So H nu naught is equal to phi. Now what does that mean? That means if your frequency is equal to the threshold frequency, then the photon has just, understand this, then photon has just energy, enough energy to eject photoelectrons and none extra energy to appear as kinetic energy. So at this particular energy, photon will make electron free, but there is no energy for the electron to move and reach collector. There will be no photoelectric current. And if nu is less than nu naught, then h nu will be smaller than phi, and the individual photons, no matter how many of them there are, that's no matter how intense the illumination, will not have enough energy to eject photoelectrons. Understand this point, I repeat, when nu is equal to nu naught, the photon has just enough energy to eject the photoelectrons and none extra energy to appear as kinetic energy. And if nu is reduced below nu naught, h nu will be smaller than phi, and individual photons, no matter how many of them there are, that is, no matter how intense the illumination, will not have enough energy to eject photoelectrons. But this explains another issue. So there is an idea of threshold frequency, right? So for all metal surfaces, there will be a threshold frequency at which energy of the photon is just equal to work function. So at this frequency and the frequency less than threshold frequency, photoelectric effect is not going to occur, whatever the intensity of light. The second issue is also resolved. Now, the third issue, the third objection, which is the time delay problem. The time delay problem is simply issued by the fact that single photon interacts with single electron. There is no question of the energy distributed. This idea single photon interacts with single electron makes that issue resolved. Because remember, in wave theory, energy is distributed over the wavefront, then there is that effective area. Electron has to soak or absorb energy from the wavefront, then it will take some time. If intensity is adjusted, that time will be adjusted. But in this photon theory, electron, photon hits electron. If its energy is sufficient, then photoelectric effect will take place, right? If not, it is not going to take place. Energy is now in bundles, it is not distributed, right? So the time delay problem is also resolved. So you can see how Einstein's theory explains the experimental findings well. So let me show you one more thing from equation 2. If we put K max is equal to EV naught, what do we get? Let me add the page. Put K max is equal to EV naught in equation 2, which is Einstein's photoelectric equation, this one. What I get? H nu plus phi. H nu is equal to phi. H nu is equal to phi plus EV naught. If we solve for V naught, we get this. V naught is H by E times nu minus phi by E. Solve for, you take this phi to the left side, it equals h nu minus phi, then you divide by e, it equals h by e times nu minus phi by e. Let me name this equation 3. Now understand this. This is the equation of a straight line, stopping potential versus frequency. You can see from the experimental curve, the experimental findings, we said that stopping potential is linearly related with frequency. So you can see Albert Einstein's photoelectric equation predicts the linear relationship between the stopping potential and frequency. And this is the slope of the straight line. You can see from the experimental curve, slope from the theory is h by e. So that means if you take slope from the experimental curve, then you multiply that by the charge on electron, what should you get? Planck's constant. The value of the Planck's constant. That was done. The slope of the experimental curve was taken, that was multiplied by the charge on electron. From this you can calculate the slope from the experimental curve, tan theta. Then you multiply that with the charge on electron, which was done. Then the Planck's constant value was obtained. Planck's constant value was obtained by other means also. Now, the value obtained using this Einstein's theory idea was also done and compared with the value obtained by other means that matched. So you can see the success of Einstein's photon theory. It explained the photoelectric effect and the experimentally gave the confirmation of the value of the Planck's constant, right? So the conclusion is now that in photoelectric effect, we know now the light has a dual character. In case of photoelectric effect, it behaves like a stream of photons. Photon is a localized energy bundle with energy equal to h nu, right? Let me summarize the lecture. First, we discussed the issues, intensity problem, frequency problem, which and time delay problem, which arise when we try to explain the photoelectric effect using wave theory. Then Einstein came in 1905 and issue was resolved by his idea that energy in this particular situation, light behaves like a stream of particles, localized energy bundles, which are photons. Single photon interacts with single electron. Energy of the photon uh, is used in two parts. One part makes the electron free. Second part becomes the kinetic energy of the photon. Now that led to the resolution of all the issues. Now so the photoelectric effect is the confirmation of particle nature of light. So I hope you got the idea. I stop here. Don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.